Okay, yeah, thanks a lot. It's great to be here. Thanks to the organizers for the invitation. It's actually my second time here in 3 months, so I'm really starting to get used to it, so please invite me again. So I would like to talk about some work which is kind of work which is about to be completed, but it's by no means complete, and there's several open questions where I'm hoping for input, and there's probably some questions where we don't even know that we have them, so please ask them so we know what the other questions are. And the title is a bit catchy. I'm not sure if it's instructive or not, but I will say in a moment what this is about. The title is really more about what motivated the work. And this is a joint work with Chris Chen, who is there in the audience, Jiaxing Zhang from Caltech, and Dominik Hangleiter from Maryland. Right, so maybe to just immediately say what we're going to do. So the goal of my talk is to discuss how difficult it is to contract a tensor network. Specifically, we're looking at two-dimensional graphs, but many of the findings, I think, should at least generalize to other regular graphs in one way or the other. So how difficult is it to compute the value of a tensor network? So it's really about computing a number, summing up a big tensor network, depending on how we choose the tensors. And specifically what we're interested in is there a fundamental difference in difficulty when we choose tensors which only have positive entries, as opposed to tensors which don't have this restriction. So tensors which have positive and negative entries or general complex entries. So that's on a technical level the question I'm going to discuss in this talk and look at it from different points of view. I have 2 motivation slides, but I think I could give the talk without a motivation. So it's a bit up to you. I think I just get briefly into it, but it's really more coming from the physics side. So there's no need to follow the motivation to ask the question. What we're discussing is really this question as a, if you wish, mathematically posed question.
Sure,
but should I motivate it? Okay, good. So I have about 20 slides, so I think we should be fine. But of course, there's an exponential number of questions one can ask. So we'll see where we get. At some point, I can give a small roadmap. Right. So what is the sign problem? Why did I put it in the title? So this comes from the quantum Monte Carlo community, where the task is to compute, in the simplest case, a partition function. So we have some quantum Hamiltonian, so a sum of local operators on a quantum spin system. And we want to compute this trace e to the minus beta h for some positive number beta. And the way this is then often done in the typical quantum Monte Carlo is to discretize this function into small steps epsilon and insert resolutions of the identity in between in some nice product basis. And then these elements can be computed efficiently if, say, in addition, we do some Totter decomposition of this term into commuting terms.
So, but you want to do trace, and normally...
Oh, yeah, sorry. This should be x1. I'm sorry. This should be x1, the rightmost term. You're right.
So...
Last one.
So...
This should be an x1, not xl.
Okay, then I'm... Okay.
So I think I just, when I typed it up, I didn't think about that, which is a fair point, definitely. Yes, no, this should be an x1 again. Right, now the idea, what people in Monte Carlo do is that they will say, let's try to do a random walk on these variables, so sample over these variables in some cleverly chosen way. And the point is, if all these terms here are positive or non-negative, then I can think of this as a probability distribution in a suitable way and implement a random walk on that distribution. Now, this basically means that what we need is that the off-diagonal terms, because there's a minus sign up here, have to be non-positive. So we're looking at operators where the Hamiltonian terms are non-positive, and these are exactly what people would call sign problem-free Hamiltonians. Or this term comes from the quantum information community, stochastic Hamiltonians. That's not really a word. It's a mixture of stochastic and quantum. So if you want to get Matthew Hastings upset, just use stochastic. He says it has been a word for 30 years. Why do these people invent another word for it?
At least it sounds nice.
Right, so if everything is positive, one can set up a random walk and sample efficiently, which is not really true. I can say a word more about that in a moment. You also have to be able to actually get equilibrating a random walk with a good equilibration time, right? But at least you don't have any negative transition probabilities. That's a good starting point for getting a nice convergent random walk. It's really a bit oversimplified, but I didn't want to spend too much time on it. Now, if I don't have this property, the Hamiltonian has a so-called sign problem, and then generally, it's much harder to simulate unless I maybe find a basis transformation, which transforms it into a basis where it doesn't have this negative sign problem. So where these things here are positive. Now, that's a problem which plagues Monte Carlo, and there's whole conferences on the sign problem. It's really a big issue, especially for computing things, say, in high energy physics or frustrated magnets. Now, then there's tensor networks, and people in tensor networks, I try to anonymize the colleagues who say that. Quite a few colleagues say that tensor networks don't have a sign problem. I probably also said that occasionally. And of course, on one level, it's true, because the sign problem is quite clearly defined by saying you try to implement a random walk, and there's a negative sign showing up when you try to get this random walk. And that's true by the very definition of what people mean when they say the sign problem. Not that they have a definition, but they will be able to tell you what's a sign problem and what's not somehow. But of course, this doesn't mean that this difficulty goes away, right? I mean, the point is the problem is not hard because this sampling, well, okay. It's a bit two-folded, right? It can be hard because, say, I'm not writing my Hamiltonian on the right basis. But the point is that, in fact, that's what people in quantum complexity have figured out. If I look at finding ground state or low energy properties of general Hamiltonians, that's a different complexity class than looking only at these stochastic Hamiltonians. And these classes are expected to be quite different. So this is expected to be quite a bit closer to NP, whereas generally this is thought to be quite a bit bigger. So the point is that tensor networks will not close a gap in quantum complexity theory. If you claim that, Scott Aronson will get very angry at you. So this cannot happen, so this difficulty must go somewhere, at least in the hard instances. It could go away in some cases. For instance, if it's a local basis change, tensor networks should be insensitive to that, but it won't go away in the general case. So this problem must stay somewhere. That was one motivation to look at what could happen in this scenario. And then if you look at these kind of path integrals or state sums or whatever you call that, you can think of this as basically a tensor network where each x, the set of configurations at one step, is like a slice, and you have several slices, so you stack one extra direction. And then this sum can basically be rewritten as just some three-dimensional tensor networks, whose entries are exactly matrix elements of e to the minus epsilon h, or the terms in e to the minus epsilon h. Now, if e to the minus epsilon h, sorry?
I don't understand this three-dimensional.
I could have done a picture, but let's do one dimension less, right? So what I'm doing is I'm starting somewhere, and then I do e to the minus epsilon h12, e to the minus epsilon h23, 3, 4, and so on. And then I do the other terms, right? So I do this discretization, then I trotterize. And then I take the trace. So if I, in addition, do some, I mean, that's a three-dimensional tensor network. If you like a different shape, you can manipulate the tensors a bit.
Looks plainer to me.
Well, it's because I started from one dimension. If I start from two, I get to three. I get one extra dimension.
Yeah, I got it now. Okay.
I get one extra dimension. So that 1D systems are typically easier, so one might have 2D systems in mind. But what one really gets is that you get a tensor network in one dimension higher. And again, if this Hamiltonian doesn't have a sign problem, which really just says that all these things have positive entries or non-negative entries, you will get a tensor network which only has non-negative entries. So when I write positive, it generally means non-negative. I haven't been very sharp with distinguishing that. Now, what typically people would do to actually contract such a network is they would try to collapse it somehow, so to go slice by slice and wrap it up, which is kind of saying you try to compress the extra dimension again to not be exponentially big. So then you would again get a tensor network with one dimension less, and one could hope that if there's only positive numbers, you can compress it to something which also only have positive numbers. Now, that's a non-trivial question. It's not clear if that's true. It's all pretty hand-wavy. It's really just a motivation. As I said, the question we look at in the end is only motivated by that. It won't really answer these questions.
Yesterday we learned that if you have plus and minus signs, sometimes that makes your problem much easier.
Oh, you mean determinants?
But match gates, yeah.
Yeah, well, we will have something which has to do with permanence later. Right, and the final motivation might be that even if you do a variational calculation, you could think of the ground set as being, there's a minus missing, as being obtained by taking some nice simple initial state and applying e to the minus beta h. And then it's very similar to this picture, just with some open legs, you collapse it. Maybe you can also do it in a way where things stay positive. This is all extremely hand-wavy, right? Because compressing needs isometries. Isometries will not all have positive entries generally, right? Because they have to be orthogonal. So it's more subtle than that, but that's trying to give a hint why it could be interesting to study tensor networks with only positive entries and ask, does it make a difference? And that's what we went out to look at. What difference does it make? Can we understand this? Finally, another observation is that Johnny and Garnet-Chan had some work where they tested the hyper-optimized tensor contractors, and one test they did is indeed involved a distribution which could be shifted into the negative numbers, and they saw that suddenly it got much more difficult to contract these networks. That was indeed the last motivation to really start thinking about that. And now, an important point to note is, first of all, this conduction is a bit hand-wavy, right, to tensor networks with positive entries. And second, even if we can fully understand this, even if this connection would be rigorous, it wouldn't definitely tell us if that's easy or hard to do the full simulation, because if you have a variational ansatz, you have to minimize that, right? So there's lots of other steps involved which could add into that difficulty. So in the end, that's really why we started doing that, but it's not, I think, what this work is actually addressing. This work is addressing the question, can we understand better why there's a difficulty in contracting, or when there's a difficulty in contracting tensor networks which have positive entries or which are not restricted to have positive entries? Yes?
What's your definition of difficulty here? Because, I mean, conceptually, contracting the tensor network is adding up a bunch of numbers, and in infinite precision, you can do it. And
I will specify it. I mean, basically, we're asking questions about the scaling, in particular with the size of the system, but also with other costs. But I will make specific statements. But right now, it's a bit fuzzy, and there's different ways in which one can branch out, and we did branch out in different directions.
You're talking about approximations, right?
We're talking about approximations generally, yes. Indeed, this slide makes the problem setting more precise. Not infinitely precise, because we look at different questions. But specifically, what we look at is a two-dimensional tensor network on an open patch, or sometimes also a periodic patch. We take tensors which have some bond dimension d. There's no physical index, right? It's just a classical tensor network, if you wish. And what we do is we draw each tensor at random, because we want to make an average statement. It's worst case, probably the statement will look quite different, where we choose the tensor first as some either H-random or Gaussian tensor, either complex or real. There's no big difference between H-random and Gaussian. It's just that the H-random one will have tails which are cut somewhere. And the H-random is also now normalized in this convention to have a standard deviation 1. So basically, it's a H-random vector multiplied by d squared. And then we shift this by a number lambda with a tensor which has all ones as entries. Right, which means we shift the mean of the Gaussian. We could have just shifted Gaussians here instead with a mean lambda.
So the all one tensor is just a rank 1 tensor?
That's exactly, I was about to say that. That's just a rank 1 tensor, and we'll get back to this question if that's an important thing. I mean, our idea is we want to shift it into a positive, and you could do this with some other positive tensor, which is not rank 1. And we'll get later to the point whether that makes a difference, or whether rank 1 is important and not positive.
So why do you prefer to write whole ones instead of rank 1? So why do you want to specify the basis?
Well, because then you can, say, put it on a computer and study it and give a plot of what you did. Or, I mean, we will have some cases where we make use that we have an all-one tensor.
Can I ask you, so this AS, there is no physical dimension. So this is a 4 tensor?
Yes.
And so H-random means what exactly? So
okay, so what we did in most of the plots I will show, the numerical tests, is to choose a H-random orthogonal or unitary. The plots I will show are for the orthogonal group vector. Right, so you take a H-random orthogonal matrix, you pick the first column, it has d to the 4 entries. So, and then you multiply it by d squared, which means that the mean standard deviation, whatever, of that thing will be 1.
no,
Right?
I thought you take a unitary matrix of d squared, and then you...
No, it's a H-random vector. I should have said it's a H-random vector, right? So you take a H-random matrix of size d to the 4, and you pick the first column. So it's really, for all practical purposes, it's a Gaussian. The one difference is that if you choose it H-random, if you shift it by d squared, it will actually be strictly positive. The other one has an extremely small tail. You can see this in some of the data. Not very much. Right, and then what we're after is to find an approximation with multiplicative accuracy. That has several reasons. First of all, say if that's a normalization of a tensor network or the partition function I talked about earlier, you want to divide by that thing. The thing you divide by needs to have a good multiplicative accuracy. There's no point in having a good additive accuracy to a number you want to divide by, right? This will completely destroy your result if that number is small. You want it up to 10% to get a 10% error.
Norbert, I mean, isn't it the same? I mean, or very similar to an additive accuracy?
No, if a number is very small. I mean, imagine you have a network.
Very small. Delta times C is also going to be very small.
No. So again, imagine this matrix has only entries +1 and -1. In the positive case, it only has entries 1. So you get an exponentially big number, right? So if you have an error of ±10, that's extremely small, exponentially small. Whereas if it has entries +1 and -1 and they're roughly the same amount, you will get something very close to 0. An error of ±10 could be 10 times bigger than the number you care about. It could even screw up the sign, right? You expect a positive result, you get a negative one. I mean, that's the subtlety of the sign problem. The sign problem is a problem if you divide by it, so to say, right? And that's why it kills you. And that's why it's important you want this. There will be no unexpected thing for additive accuracy, or little unexpected things for additive accuracy. There's a difference in complexity as well. Right, so then the question is, how hard is it to approximate, on average, say, over such a choice, this value up to some given multiplicative accuracy? And of course, that's indeed a fuzzy question. So one question could be, given a specific algorithm people use in practice, will this algorithm be sensitive to it? You could also ask worst case questions, right? What's the worst case complexity? Is it impossible to find an algorithm which is more efficient than something? There's a range of questions. We will look at some of them. We have some results I don't mention, smaller ones. There's some known complexity results on these questions. In particular, there's known worst case results. There's a reason we look at random average instances, right? Worst case, these things are typically very hard. They're easier, I will say something in a second about in the positive case, but they're still hard. And of course, an interesting question is, how much do I have to shift this distribution to the positive to make things easier if they get easier? But we already have this kind of hint from Johnny's work that they should get easier. So the question is, how positive have these numbers have to be for things to become easier? So that's kind of the complex of questions I would like to look at.
So just a comment. I mean, it seems like a lot of what you're doing here is what numerical analysis people have been doing for years in terms of bounding the relative error you were talking about. That's their way of measuring.
No, I mean, asking this kind of questions, that's something which has been done a lot, right? The question is, in this specific context, how much is known? I'm not sure much is known, but it could be. I mean, I would be very curious to know about results, really, or even techniques to get more rigorous results on that. I mean, partly more rigorous, but also kind of a more clear understanding why things happen. So in particular, we will see there's entanglement transitions where we don't really have a mathematical formal way of understanding why they happen in the general case. Right, so what we have in the tensor network, we sum over all the indices, right? And for each index value, this thing is easy to compute. So it's an exponentially big sum. And this sum, even if the numbers are positive, is exponentially hard to compute, right? It's counting, basically. It's a general case of counting solutions to, say, a satisfaction problem. So it's this class sharp P, which we have heard about already a few times this week. And now if I want multiplicative approximations, and that was actually one reason why I felt one could say more about this, because I knew about these results. If I want a multiplicative approximation to a counting problem, a sharp P problem, if I'm adding, so if it's really counting, I'm adding only positive numbers, the complexity is very different from a counting problem where I'm not really counting, but adding up positive and negative numbers. Namely, for positive and negative numbers, these approximations still remain as hard as the original problem, basically. Whereas if I only have positive terms, they get much easier. And the intuitive way to see that is that you could do Monte Carlo sampling. And again, you have to find a good random walk. But that might even be intuitive, that it might be easier than the full counting problem to find a good random walk. You might need much less advice. But famously, there is a result in complexity theory from 82 or 83 by Stockmeyer, who shows that basically I can find a randomized algorithm which only has to query an NP oracle. What does it mean? It needs to access to a machine solving decision problems, yes, no questions, saying, is there a solution, which is much easier than counting, right? So you can replace counting the number of solutions by just asking, is there a solution a couple of times? And this will allow you to approximately count, to estimate that number. So we indeed expect that such a positive sum should be much easier to compute approximately, even if complexity theoretically, that's still a hard class because it's harder than NP. It's still also much easier than this full counting class from all we know from complexity theory. So that's one motivation why we really expect this to be easier. And one thing one can look at is indeed how does this manifest itself in something like Monte Carlo sampling. So the first thing we looked at is if we would contract this tensor network by sampling over this sum, how would this converge? And the thing people typically look at, I mean, that's really the starting point. What we're more interested in is in the way people actually contract tensor networks. And no one contracts tensor networks doing Monte Carlo sampling. It's a good question whether that would be in some way a practical method in some cases. I think it's an interesting question. The answer is probably no, but it might be worth thinking about it for a while.
I don't understand how you're doing this Monte Carlo sampling on a tensor network, what that means even.
Well, okay, I don't know exactly either. I mean, you need a way to actually get the random walk done, right? Which is non-trivial.
Well, let me grant you that you can do a random walk and whatever else you want me to grant you, but I just want to know what you're doing. It's a very basic question.
Okay, so the idea would be that I choose specific values on each of these legs, right, 1 to D, and I do a random walk on the space of these configurations. For each fixed configuration, every tensor just contributes a single number. I can multiply them, right? So I can basically sample. So that's what I call Tx1 to xn, is a value I get when I put a specific assignment to each edge, right? And if I can do a suitable ergodic random walk, I will be able to sample these numbers and then get an estimate of that with some 1 over square root of number of sample points precision, right?
So it's like when you want to compute the trace of the matrix, you just say I sample random x and I look at xax.
Yes, yes.
Like
Well, in that case, random means basis states, right?
yeah.
But what you said that so you do this random walk and then you sum what you get. No, I don't get it.
You do a random walk, and for each point of the random walk, I mean, you need kind of either you make a completely flat random walk, that's easy, but probably not very nice, or you find a smarter way to sample, right? But I mean, doing flat sampling definitely works, and we'll have a 1 over square root of k times some standard deviation convergence. I'm not suggesting to do that. It's just a way to look at, I mean, basically what I want to understand is something about how does shifting the thing to the positive affect the cancellations. I mean, what's the problem with summing positive and negative terms? There's cancellations, right? So I want to know how strongly is this affected by this lambda. Oh my God. I think it's... the secretary is shocked. Oh, Steve White has a question, and I can see him. Steve, hi.
It didn't show me the
I can't
hand
hear you,
raising
Steve.
up.
Wait, I think we have to...
So I have a question. So
maybe it's
in
because the
Monte
speaker's
Carlo,
off.
oh, can you hear me?
Ah, now, yes.
Okay, so in quantum Monte Carlo, there might be a big difference between doing a quantum sampling that measures some property of the network, some Green's function, versus trying to get the whole partition function. It seems like we don't know how to get the partition function, but we can get some observable. And does that enter into what you're doing?
That could be. I mean, I'm looking at the partition function basically here, so I acknowledge there could be a difference. Anyway, that's not the main focus. I mean, the focus here was really in the partition function sense. Is there a transition in the difficulty?
Good.
Okay. Good. Can you switch this off again? Just so there's no unexpected questions. No, I'm joking. Okay, right. So what people in quantum Monte Carlo do in these cases is actually to look at something like this. So they say, let's look where we sum the absolute values, right? So that tells you how big the numbers are I'm adding in total. And compared to this sum, which has a cancellations, and look at the ratio. And you expect, certainly for such a random tensor network, that this would scale extensively with a volume. So there's some delta F, and delta F, they call it the free energy difference between a fermionic and a bosonic wave function.
Where's F coming from?
I define the left-hand side to be this, right? For a lattice of size n. I claim this is extensive. Otherwise, delta F will depend on n, but if you actually compute it, you will see that it's the straightest line you've seen in your life. Well, maybe not, you're a mathematician, but it's a very straight line. No, it's a definition, right? I'm saying this quantity, you expect it under some nice extensivity condition to scale extensively.
The symbol delta, is that a...
That's a name. It's called delta F because it's a difference of two free energies. That's how people call it.
Okay, so you're defining delta F by this.
Yes, exactly. I'm defining delta F by this, and you have to check it's a straight line, and it is.
The log of the right-hand side.
I mean, it's natural to expect it has a scaling. Okay. So that's what we find if we compute this delta F for different bond dimensions and either unity or orthogonal random vectors. And there's two noteworthy things, maybe. One noteworthy thing is that there's around lambda 1 over d a point where the severity of the sign problem, so how much cancellations you have, saturates to a value, and the saturation value will be bigger for bigger bond dimension. So kind of the sign problem gets worse for bigger bond dimension, and it saturates at a value which is pretty much log d. I have some plots where you can subtract log d, and they collapse amazingly well. The second thing worth noticing is that even after that, this number is still macroscopic, right? I mean, it's on the order of 1 per site, so you still have a big sign problem. But here, this tail decays very rapidly, and particularly for the orthogonal group, it decays exponentially. So you could well argue that if your lambda gets somewhat bigger than 1, which means you've shifted this distribution significantly to the positive by at least a standard deviation or so, the sign problem will go away, right? There won't be a big cancellation due to negative signs. That's certainly plausible. So you could think there's three regimes. There's one where the sign problem gets worse when you make d larger. There's an intermediate regime, which is d independent, where the sign problem is d independent. These curves all collapse nicely. And then if your lambda is quite a bit bigger than 1, the sign problem will go away, at least in some sense. So let's keep this in mind. What we see here is that it really only goes away when we shift by at least a standard deviation or so. Yes?
Some numerical result on some
That's a numerical result, yeah. That's a numerical result on a big system,
okay.
Very big system, extremely big system. And basically, I'm going forever in one direction and keep updating delta F. And then you have to normalize every time, because otherwise you immediately 10 to the minus 300, and then your numbers are gone. It's pretty straightforward. Now, that's not what people do in tensor networks, right? They don't Monte Carlo sample. What people do in tensor networks typically is that they start taking a column from the left, and then this column here, they approximate again by a matrix product state with some dimension chi. Right? And let's not care how this is done, but this involves some cutting, right? Because if I take a big block here, I will cut many bonds and I want to compress them. So eventually, if my network is big, I will have to cut. And then what we want to look at is what is the error we induce by cutting. So there's an error which we get in some suitable norm, which we get by cutting. And the computational cost hopefully should scale polynomially in chi. So we want this chi not to grow exponentially with our problem size. And then we're in kind of a safe regime where we have an efficient way of solving the problem. And now the real question is, does this method also have a transition? Well, there's some evidence, right? But for this specific distribution, and then the question, I'm not sure we had this question, but now it's natural to ask, where is this transition? So how do you look at this transition? Well, what you want to do is you want to take this boundary state here and ask, what is the error I incur by cutting it across some cut here, right? By cutting the bond dimension, which relates to taking the Schmidt coefficient in this cut, so the singular values of this tensor psi ij, I is for here, j is for here, or eigenvalues of psi dagger psi. There are probabilities if I normalize suitably, and I better normalize suitably. It's not a quantum state, right? It's just a tensor. I have to normalize it by hand. So then I get some probability distribution, and I cut it at some chi. So what I care about is the weight in the tail. That's the error I will incur, or maybe the height times that error. But this will not make things change. They're scaling polynomial versus exponential. Now, ideally, I should keep the full information about all the Schmidt coefficients, because this will tell me everything, or the weight of the tail, right, the ordered Schmidt coefficients. Now, that's maybe a bit too much information. So what people often do is they look at the entropy of this distribution. Because if the entropy is small, it's very peaked, and you will incur a small error when you cut. Right? If the entropy is large, it's very flat. Now, there's a lot of different entropies, Renyi entropies one can use. Now, what we will use, most people do that, is a 2-Renyi entropy, and there's not really a strong reason from the point of view what you want to look at, but it's just a thing which is nice to compute and analyze, and that's a real reason to look at. It's not ideal because it puts too much weight on the smallest Schmidt coefficients and not enough weight on the tail. Yes?
And like if you want to bound the bond matrix, then you need alpha smaller than 1, right?
Exactly. I mean, if you want a technical result telling you that, that you have a nice scaling of chi, so chi grows polynomially with the size or so, then you indeed want that to have this area law for an S alpha with alpha smaller than 1. I mean, of course, the folklore is that all the entropies behave the same, and I will tell you on the next slide or so that they don't in one regime, and we don't fully understand what's going on. And I would be happy to receive input on that, actually.
So,
but let's...
I think you just said this, but I didn't quite pick up on it. So what is the role of alpha in
I mean, definition-wise, this one.
No, I understand the definition.
Okay, so there's a theorem which tells you that if for S alpha smaller than 1, if you have a height h here, if the alpha entropy for alpha smaller than 1 grows at most logarithmically with the height, then the epsilon of chi will scale polynomially in chi. No, the other way around, right? So what you get is that the chi you need to achieve a certain error will scale like 1 over, will scale like poly 1 over epsilon and h.
So chi is the bond dimension.
Exactly, for cutting, right? Not the PEPs, but what you truncate. So we're truncating this psi ij in all cuts. You ask what bond dimension do I need to get an approximation quality epsilon on a system of height h. And this will scale polynomially if, but not only if, maybe only if, I have to look it up, the S alpha of the thing in any cut scales slower as C log h. You need a sequence of steps really to make a scaling statement. Sorry?
For alpha smaller than 1.
For alpha, sorry, yes. I wanted to write it and then I forgot exactly. For some alpha or any sum, right? The alpha 0 is the easiest. It tells you the rank is growing logarithmically, the log of the rank, right? So then you're definitely fine. So that's not really strong enough to give a proof, but we anyway analyze it numerically, so it will anyway not give a proof. The thing is just it's much easier to compute, right? Because you have to take the thing to square it and take the trace. You don't have to compute all these eigenvalues and then take their logarithm. So it's just significantly easier. And then again, a single Renyi entropy only gives you limited information. You really care about the scaling. Okay, so that's what we get when we shift this distribution here and we plot for a fixed bond dimension and different system sizes the behavior of the entropy in the middle cut, which should be the hardest. Now, unfortunately, I didn't put the other plot here, but it turns out that, I mean, you can see there's a very sharp transition, which is pretty much independent of the width. It gets kind of sharper as the width gets bigger. And it happens not at lambda equal to 1 as a Monte Carlo transition. It happens at lambda times d equal to 1. And that's something, maybe I should have also put the other plot. I have it if you want to see it at the end of the slides. If I plot this for different d's, and you plot lambda d, they will also all coincide. So indeed, the point where this happens is at lambda equals 1 over d, as opposed to lambda 1 for the Monte Carlo. Now, I think this is extremely amazing, and I don't really understand it. I mean, it's some concentration of measure, and I can say these words, but emotionally, it feels like very strange. Because you're shifting this thing here by this is standard with 1, right? You're shifting it by 1 over the bond dimension. You're shifting it by almost nothing, right? I mean, the weight in this part here is super small, right? I mean, you're shifting it by 1 over d or so. And you have to shift less and less the bigger the dimension gets. So it's one of these extremely puzzling concentration effects for high random states, but I think it's very puzzling. So basically, you need less and less positivity in the distribution to get efficient contraction if you do this entanglement-based contraction, or a small amount of correlations, the bigger your bond dimension is. I think that's kind of remarkable. We didn't expect, well, I didn't expect it. I found this very puzzling. So, I mean, that's one thing where I really would be happy to get some more insights. My suspicion is that there's some results known in the random matrix community, singular values of random matrices. And of course, it's a tensor network. It's a bit more complex, but maybe there are some results one could apply here to gain more insight. And if someone knows something about that, I'd certainly be extremely excited to hear about it. Now, one thing I should point out briefly, but I don't have plots or anything. There's a strange feature here, namely the bigger width has a smaller entropy on the right of the transition. You can see it here. Now, if you would take this and zoom, which basically means take a log axis, you would see that the effect is here even much more extreme, which tells you that, that the distribution of Schmidt coefficients is getting extremely peaked, right? That's kind of, if you actually look at them, that's the intuition, right? Because S2 tends to overweigh the leading Schmidt coefficients. If you actually do a plot, you find that they decay extremely rapidly. The tail then is actually slower than in the other phase. But they decay extremely rapidly in the beginning, and it's more and more rapid. So we checked some data yesterday, actually. If you go here, the first eigenvalue is basically 1. The next is already 10 to the minus 6 or so. It's completely crazy how strong this concentration effect is. And it gets bigger for bigger dimension. So there is this transition. You can see it if you look at other cost functions, even though it's not properly mapped out by this 2-Rényi entropy. But it's puzzling, it's so strong. I think it would be very interesting to understand, if one can understand the features of this distribution better, in particular in this positive regime here, right? Exactly, in this positive regime here, where there's this very unintuitive behavior that if I make this wider, meaning I cut more bonds, I get less correlations and not more. I think that's very puzzling. Right? I mean, you would think you cut a bigger tensor network, there's more correlations. They shouldn't get less.
But you also this hard random average, I guess.
No, there's no. That's a specific instance. I'm computing data points for one random instance, but of course it means every tensor is chosen random individually, right? So there's some averaging involved. But I'm computing one specific instance. That's averaged over 50 instances. So the gray strip is where the data points scatter. So that's the standard deviation of the data. And the green one is the standard deviation of the average.
Maybe you can interpret sort of this as some random time evolution that you apply sort of to your initial column, right? And for this, and this sort of disentangles in some way.
Yeah.
I don't know.
Yeah, let's see. I have like 15 minutes or so, I guess. That's roughly accurate. The chairman is too fascinated too. I have like 15 minutes or so. Is that What's 12? 20?
No, 12.
Well, I mean, it's 50 plus 10, but there's lots of questions. But there's always lots of questions. Okay, so I think I will skip something, but let me say one thing, which is a bit related to your evolution question. So one thing we wondered is how can we explain this entanglement transition? And one explanation we tried to come up with, which sounded very cool, was to say, well, there's this sum, there's this random Gaussian, and there's this rank 1 tensor, right? So what you can say is you can expand this tensor AS, you can expand this sum, right? So you have a lot of terms, and in each of these terms at each side you either have a G or this rank 1 identity tensor. So that would be a typical realization or so. So if you have a lot of identity tensors, there's no correlations really in that configuration, right? At least no big correlations, because these are all rank 1 tensors, right? They just cut it apart. And then, of course, you have a big sum over rank 1 things, but maybe you're lucky and they don't add up too much. But then if you think, that's something which people have looked at in things like measurement-induced phase transitions and so on. So it would basically be a percolation transition somehow, right? You break the network apart.
In that case, it's edge percolation where you have now a kind of vertex percolation.
It's probably vertex. Okay, you mean in the measurement-induced phase transition? Yeah. No, I'm not saying it's the same. Actually, it's also not what is happening, because if this would be true, you would expect that it should not depend on the dimension, right? It's not clear why there should be. Well, it's not entirely obvious, because there could be an effect from fixing normalizations, but it doesn't seem very plausible that it depends on normalization. The good thing is you can just test this numerically. You can replace I, there was this question, you can replace this I by a different rank 1 tensor, which also has negative entries, or by a randomly chosen positive tensor, right, which is not rank 1, right, just positive. And that's what one sees. If you interpolate to a purely positive but not rank 1 tensor, the transition is basically, again, somewhere at lambda times d equal 1. It's not exactly 1, but it depends how you normalize your randomly chosen tensor. And even worse, different bond dimensions have different randomly chosen tensors, right? So it's hard to compare things. One would have to do a randomness average here.
So
that's really only one realization.
Once again, what it was, this transition?
Okay, so the overall point of the transition is to ask if I take part of my network, right? I take a network which has some width W, and specifically what we took is 2W and 2W, but you could take this very big. It doesn't make a difference, we checked it. I just want this to be the narrowest part. And this is a matrix from here to here, right? If I contract all these tensors, which are randomly chosen, and they're randomly chosen according to such a distribution, Gaussian, and then the shift. And then I'm looking at the Schmidt coefficients, or singular values in this cut, right? And specifically, we look at the entropy, but the more general statement is the way in which they decay changes very quickly around lambda times d equal 1. I mean, specifically, what we plot is this 2 Rényi entropy, but you can look at the actual Schmidt coefficients, and you look at them, you see they're, I mean, I can show you they're completely different, right? The way in which they decay. So basically, it's about the distribution of singular values of this matrix here, which is obtained by contracting a lot of tensors. So it should be related to random matrix theory, just that there's this big contraction. It's not a single matrix with random Gaussian entries. That's probably known what the singular values of that are or how they behave. But it's many matrices put together. Yeah?
Maybe I missed something. Can you just explain what you mean by interpolating to only rank 1, only positive? So what are you changing?
OK, instead of the I, right, which is rank 1 and only positive entries, I either put something which is only rank 1 but has half positive, half negative entries. Well, I mean, you care about scalar product, so it's a little bit more subtle, but it's basically completely unbiased with positive, negative. Or I only put some random tensor, full rank. Well, I guess if it's random, it should be full rank, and do the interpolation. Only positive, sharp transition at lambda times d equal 1. This one, that's a lambda axis, and there's not even a sharp transition. It's more like the Monte Carlo observation, so to say, right? It just smoothens out. So, I mean, you expect a transition around 1, because then the percolation argument will probably be accurate, right? If I put a lot of rank 1 things, the thing will just fall apart. Okay, so what can I do in remaining 10 or so minutes? I could either say something about an effective model, which allows to understand why the transition should be at lambda times d equal 1, but that's maybe a bit heavy on statistical mechanics. Or I could briefly sketch a proof which works completely differently, which tells you, but that's actually a proof, well, I would sketch only the idea, that one can actually approximate the value of the tensor network in this regime up to lambda times d equal 1. Maybe I sketch the proof. I think it's the idea is super neat. Okay, that's a StatMech model. That's probably a bit lengthy if you've never seen StatMech models. But exactly, so can we rigorously prove efficient approximability? That's a question. And so what we have, again, just to remind you, right, we have this Gaussian tensor, we have the identity, and now instead of putting a lambda here, I put a z times d here. Z will be a complex variable. It's the same thing, right? If lambda times d is equal to 1, it's the same as z being 1, right? Because then I have a d here, which is a 1 over d if I move it here. So z equal to 1 is kind of what would be the transition. Z equal to 0 would be lambda to infinity. It would be just the identity tensor, which is trivial to contract. And the idea now is that we say, well, let's think of the contracted tensor network as a function of the shifting parameter, which shifts from the trivial tensor network with all ones everywhere, to the one we actually care about, which is, say, z equal 1, if we want to aim for this lambda equal 1 over d point. And what we want to look at is the logarithm of this function and get an additive error, right, which is the same as multiplicative for the function. And the idea now, and this goes back to an idea from Barvinok, or a result from Barvinok, how to approximate the permanent when the permanent is hard to compute. But Barvinok showed you can approximate it efficiently with a high probability if you have entries which are close to 1, and not super close, 0.2 or so. And so the idea is that you take this function f here, and you do a Taylor expansion up to some not too high order. Now, what does it mean if you take the log derivative of that? It's a ratio of derivatives of this function and this function at 0. Now, at 0 means you only have identities. That's easy. every derivative will give you a random Gaussian tensor, right? So if you take some derivative, you will have a couple of Gaussian tensors, but not too many. The rest is identities. So you can compute this exactly, right? And efficiently, because you only get small clusters of these random Gaussian tensors, right? As long as your order is small. You can see this with a Taylor argument. This can very likely be improved if one uses some cluster expansion, right? The idea of Barvinock, there's no lattice, right? It's a permanent. So probably here one can actually even improve the result by using better expansions. And the point is one can give error bounds. So what you need, of course, is that this doesn't have branch cuts, which means G shouldn't have zeros in a circle around 0. And then you can get a good approximation in a somewhat smaller circle, right? I mean, the first 0 will tell you how bad your error will scale if you truncate a Taylor expansion. And to actually get a good result, you have to go one step further. That's one thing which Elder and Mehraban did. You really have to do some kind of analytic continuation. So you take a first circle where you can guarantee there's no zeros. You do a Taylor expansion. This you use to expand the next circle, and then you move on. So you want to build a channel. You could even build some kind of twisted channel. It doesn't have to be a straight tube. And along that, if you can guarantee there's no zeros, you can make an estimate of your function. This has all nothing to do with the problem we're actually looking at right now. Well, this part has, right? But the fact that you can do this with tubes, it's a general statement. So you have to find a tube, which basically means you have to find a circle around 0 and then some direction, some slice of the cake where there's no zeros, and then you can build such a tube. And the key idea how this works is there's a lot of Jensen involved. That's very cool. It's different results from Jensen. The one thing, and I think this is all magic, complex analysis is just beautiful. You can bound a number of zeros by this integral over this function, so the zeros of G, which is the branch cuts of the log of G, by an integral over a unit, over a circle of this function, or the square of this function, actually. Doesn't matter, it's a log, right? And there's some constant which depends kind of how far the circle and the circle where you look for zeros are apart. And then you can, so that's Jensen's formula. That's Jensen's inequality. You can pull the log out. And then you can take an average, right? And again, with another Jensen, you get the log out of the average. So what you're looking for, you can bound a number of zeros by computing the expected value over the Gaussian randomness of your tensors over this integral. And the magic, and I won't have time to talk about that, but I'm happy to explain this. So there's not much explained here because it's one of the slides before. You can use standard techniques from doing randomness averages over Gaussians, right? If you do a randomness average over 2 copies of a Ha unitary or Gaussian state, you get basically deltas. Now, our tensor is a shifted Gaussian, right? So what you get is that you get a non-shifted part, which is the identity tensor, and the average of the Gaussian, which is delta tensors. So on each side, when you average, you get 2 configurations. And you have to take overlaps. And if you've ever seen that, this is somewhat standard. You can say this is one configuration at the lattice side, that's a different one. You expand the sum in these 2 configurations. And they interact exactly via an Ising Hamiltonian. Well, you have only 2 states. You can't get much more than an Ising model if you have 2 states. So computing this can be mapped back to computing a partition function of a classical 2D Ising model. Unfortunately, not at 0 field, because there's an exact solution for that. But one can still bound the relevant quantities to get a bound on this quantity, which gives you a bound on the zeros. And then if the chance of finding a 0 is 0.0001, you know that in most instances, you will find a circle without a 0. That's a basic idea. The hard work then is in particular in finding these bounds for the Ising model partition function. And this really gives you a rigorous statement that you can find almost, it's not exactly polynomial, it's quasi-polynomial, but the same is true for Barvinock's method, algorithm which works all the way in the language of original lambda for any shift of the Gaussian, which is bigger than 1 over d with a very small correction. So it really gives a proof for the same boundary we find for the entanglement transition. And I think that's really magic, but it's a completely different approach. The one thing is you have to increase the bond dimension. It's not entirely surprising because all these arguments work in some, I mean, if you want to say they work with super high probability, you have to go to a large d limit because then fluctuations get smaller, right? You get like, what's the word? It doesn't come to my mind. You get this kind of limit where large deviations are extremely suppressed, right? If you take H random states in high dimensional spaces, it's typicality arguments. It might be that one can decouple the limits. In this case, there are coupled limits, so d has to go with the system size. But then, indeed, for any shift larger than 1 over d, which means this thing is only very slightly positive, we can show that there's an efficient algorithm giving an approximation to 1 over poly accuracy. And it works with a probability which approaches 1 as you make your system bigger and bigger, which is exactly the point over this Gaussian randomness. And yeah, I think that's probably a perfect time to stop. If you want to know more, there's something about how to understand the 1 over d transition from a mapping to a statistical mechanics model. And I also have something about why it should be easy to compute expectation values of actual physical tensor networks, which have legs pointing up in addition, right? So you would have a cat-bra sandwich of that type. And that's, again, efficient because there's a hidden positivity in these things, which remarkably can be used. OK, thank you.